So I'm gonna. I'm gonna give you a couple more results about. Yeah, I'm gonna give you a couple more results concerning integrality, and then we're gonna move on to valuation domains. And do a more extensive look at those, and that might seem like a total kind of non sequitur, but it's not. Because the valuation domains that we just briefly touched on earlier actually are very intimately connected to the notion of integrality. So we do the following. Suppose a family of integrally closed domains all contained in some large domain T. So assume these are all in some kind of universal domain T. Notice that if I'm going to say integrally closed, domain is sort of implied because integrally closed means you're integrally closed in a quotient field. So you're going to need a domain for that in the first place. So you've got all these domains like Z or like UFDs and so forth that are integrally closed in a quotient field. Then the intersection of Ri is also integrally closed. That's kind of a nifty little result that if you intersect a collection of integrally closed domains, that's integrally closed. A little underdressed here. So let's see why this is true. I mean, one thing that we do know is an intersection of a bunch of domains is a domain, right? Subrings of domains are domains. Subrings in the identity sense, all of these contain the same identity. It all contained in this master domain P. So this is actually an integral domain. It's got quotient field K, right? And suppose omega is an element of this quotient field. If omega is integral over R, we don't find the equal same section. So if omega is integral over that, then omega is integral over each. And here's the reason, right? So suppose that omega is integral over R, right? That means it is a root of a monic polynomial, all of whose coefficients are in R, but each one of these R's is contained in Ri. So one can construe their coefficients as actually being in Ri, and that's why omega is integral over beta, right? In fact, there's a general principle here. If omega is integral over some domain, it's integral over any domain that contains it. But each Ri is integrally closed. So omega is in Ri for all and except therefore omega is in. So it's okay. let me throw in this, theorem here. Which I won't prove, and you'll quickly see why I'm not gonna prove it. I've actually had to do this before, y'all did this as a homework problem, but I recorded here for your notes and if we're going to use it later. Let R be an integral domain, then R is equal to the intersection R localized M. R is the intersection over all localizations of R at maximal ideals here. Let me throw in a quick bit of notation. If R is a ring, then spec R. How many of you have heard of this notation before? Some of you maybe. This is it's the spectrum. Unfortunately, spectrum shows up in a lot of fields of math using kind of different sort of. Like this is a collection of P and R. So when you talk about the prime spectrum of the ring, all you're talking about is a collection of prime ideals. And max spec is collection max. So if I ever use that terminology, that's what that means. I'm gonna give you, I think what's probably the last proposition before we move on into valuation domains. Proposition. And this is, as you might think, this is quite nice because integrally closed commutes with localization in the following sense. If R is closed, so again, I'm really talking about domains here because it's implied that there's a quotient field here. And S is a multiplicative subset. Here we will assume 0 is not in S. So that we don't get the 0 ring. Okay, so here's what happens. You start with a ring that's integrally closed. So it's integrally closed in this quotient field, more specifically. And you have a multiplicatively closed subset, then this localization, this field of fractions is also integrally closed. Notice that this is a silly result if S is all the non-zero elements of R, because then this is a quotient field, which is of course integrally closed in itself, because it's already got everything in the quotient field. Any ideas on how to do this? So let's suppose that suppose you have an element in the quotient field, and suppose that it is integral. Right. suppose you have some fraction in the quotient field. Here, we'll assume that A and B are in R. Right, because K is the quotient field of R. And notice K is also the quotient field of R localized at S, right? Because R localized at S is between R and quotient field. So this animal and this one have the same quotient fields, namely K. Okay, so what does this mean for A over B? The integral, so notation again. So there's some equation like this with the Ri's and R and the Si's and S, right? So it satisfies some polynomial equation, monopolynomial equation over the ring R localized S. So what I want to do here is so I guess what I can do here is okay, so I actually let's take this through what we want here. So let's multiply through by the appropriate denominator. So I'm going to just write this down, and then we'll see if we can kind of justify how I got there. So I want Tn let's see. So I included some denominators here, and each of these TIs are in S. How can I do that? Well, what can I multiply by? Well, in fact, what can T to the N be? Right, it's really all I've done to go from here to here is I've stripped off the S's, right? The only thing left in the denominator is B's, right? So how do I strip off the S's? Well, I mean, I could just really go bananas and go Sn minus one, Sn minus two, all the way down to S0, multiply that thing, and that'll do it. And so, for example, Tn would be the product of all those S's. And Tn minus one would be the product of all those S's divided out by Sn minus one. Am I okay with that? So the important thing is now I have got this to an equation that is now all the terms are in R, right? A over B, this is a polynomial equation, A over B, all the terms are in R. However, one thing is troubling, and that is it's no longer monic because I've got that Tn hanging around in the front, right? Well, I've already used the bulldozer, so let's get out the backhoe and fix that. So what we can do is actually now we can multiply both sides by, let's say, I guess T to the N minus one. Everybody okay with that? And now, so this is kind of a neat little integrality trick here. What I want to do is I want to kind of absorb the appropriate powers of t to the n in there that I need. Notice that first term is now t to the n able to be the n power. Right, because this is just one giant n power here. I want to suck the t to the n's in here. So I get t to the n minus 1, r to the n minus 1, t to the n a over b, the n minus 1 power, right? And I keep going. And now, I mean, as I go down, I need less and less power with t to the n. So in fact, in the second last step, I have t to the n minus 2, R1, T1 R1, t to the n a over b, plus t to the n minus 1, T0 R0 is 0. All right. So what have I got here? What does this allow me to conclude? And so, what do we know about R? R is interval flows. So, solve this equation. And this, that's an R, this is an S. So this is an R plus S. So my AB, my original element, was actually already in the localization, which gives me a warm, fuzzy feeling inside. Any questions? Right. So there's kind of a first look at integrality. So we're going to play this off of valuations, and then we're going to come back to even a more sophisticated look at that. But any questions before we move on? Let me ask you. So I wanted to ask one more question. John, did you have something? Oh no. So here's what we showed. You know, the mathematician, he always says, okay, got a theorem, I'm so proud of myself. What about the converse? What do you think? No, not in general, right? I mean, obviously, this is going to work in some special cases, right? For example, if S is the set of units of R, right? I mean, that's kind of stupid, right? But then RS and R are the same thing. But so here's an extreme example. If you look at we've seen that this one isn't. This is not interval closed. However, I call this R. Then R localized S is QI, which is of course a field, and any field is interval closed, right? So this inspires questions, right? So one might ask the following question: for what types of sets S do you accomplish? Okay, questions. Okay, so Okay, so here's, by the way, I told you what valuation domains are, right? For all A, B, and B, zero, then A dot B or B dot A. But, you know, the choice of the terminology valuation domain might seem a little puzzling. Where in the world does that come from? And we're going to see that because there is something called a valuation that determines the valuation domain. A valuation domain is one where given any two non-zero elements of the domain, one of them divides the other. Or another way to think of it is given any element of the quotient field, not zero, either it, actually you could include zero in the statement of it, either it or its inverse is in valuation domain. So for all omega and k, either omega or omega inverse, it's an element of the domain. Theorem. Let me record this because this is all nice to know. Most of this is not reversible, right? So let B be a valuation domain, then B has the following properties. B has the following properties. And when I say most of this is not reversible, in fact, I'll note if any of them are reversible. For example, the first one, B is quasi-local. And what I mean by not reversible is if you walk into a quasi-local domain on the street, odds are it's not a valuation domain, right? But every valuation domain is quasi-local, and remember what that means is has unique maximum deal. All valuation domains are integrally closed. As a matter of fact, here's another one. Every over evaluation domain. Wow, that was a big one, right? So what that means is, suppose you start with some domain, and suppose you start climbing toward the quotient field, and finally you get to like 10,000 foot base camp or whatever, and you look around and say, hey, I'm at valuation domain 6, right? As long as you keep climbing up from there, it'll always be valuation domains all the way up. So once you reach valuation domain forever all the way to the quotient field. It's kind of cool, right? Almost any other property you have rings, probably not going to happen. There are other domains that is property. For example, proof of domains. We'll talk about that later. Every overring. Is a local extension. Again, this is very unusual, right? It's, you know, a garden variety. So for example, one of the simplest domains that I can think of, well, at least from some points of view, it's not a simple domain, but polynomial ring over field variables. Actually, you don't even have to go on forever. That overlay is not a localization. Right, there's no way that's a localization. We did find other kinds of domains that satisfy this. Every overlay is a localization. Can you name a class that's not necessarily valuation domains? Where every overlay is a localization? PIDs have this properties. And PIDs are usually not valuation domains. Number 5. Every finitely generated ideal is principal. So there might be ideals that are not finitely generated, but every one that is finitely generated can be generated by a single element. 6. All prime ideals. In fact, all ideals of B are linearly ordered. By the way, given the definition of valuation domains, it's probably not too surprising that all the principal ideals are linearly ordered, but all ideals are linearly ordered. So in particular, prime ideals are as well. And 7, if I and V is an ideal, then the radical of any ideal is prime. Now, in general community case, the radical of any ideal is radical, right? But that doesn't mean it's prime. An evaluation of it. So, I don't prove any of this. I'll probably ask you to do some on the next homework, which I probably will be out soon. Okay, somebody vote. What's the weirdest one? We'll see if we can prove one of it. What's the one that's too weird for color TV? I don't care. Whatever your taste is.
I'd like to see 6.
Like to see 6. Okay, so certainly if all ideals are linearly ordered, then all prime ideals are linear. So let's do this. If I prove all ideals. No. All ideals. So to this end, I'm going to do my contradiction, I guess. Suppose now what statement 6 says is that any two ideals are comparable, right? One of them contains the other. So if this is not the case, suppose we can find two ideals such that I is not contained in K, and K is not contained in I. Right? So there exists, let's say X. Okay, so I is not contained in J, so there's an X that's in I, but not in J. And because of this other condition, there's a Y it's in J, but not I. Correct. Now, notice that X and Y are non-zero. Because of course 0 is in every ideal, right? So without loss of generality, X must divide Y. right? Because it's valuation domain, one of those animals got to divide the other one. Therefore, let's say that y equals vx, son, v, and then that's what it means for x to divide y. Therefore, y equals vx, which is in I, which is because y was chosen, but not. So that means you got any two ideals, you gotta be able to compare them. Super groovy. Okay, Wolfman Jack, we'll take one more request. We've got a prime idea here. Do I want to request one more? Four. Oh, every other one brings localization. And we got to show the W. So we need to show. Yeah, here's one. How we'll do that. So we're given an overing W. And of course, if 4 is correct, it must be it must be a localization of V. And so there must be some multiple set S that does the trick.
We just do the same thing you did in homework, like for general.
It's a great idea. That's exactly, I think, what we should do. So the trick is to find what S is going to do the trick for us. So what S, well, it should be a subset of V. So take all the units in W that land down in V, and we'll let that be there. Now, I guess really we need to show I claim W is equal to VS. My guess is that's going to be the easier. How are we going to do this? Well, suppose D over S is delocalized S. Okay. So, of course, what I mean by this is in D, S is in S. Right? Since S is in S, S is in the unit W, right? And so how does that help us? Okay. And B is contained in W. Therefore, B times 1 over S. So that's established. Okay, so let's try to get the other one. This is always the fun one. We're gonna do that. Well, I do know this. I know the W. That I know for sure, because we did say overrange, so whatever that W is, it has to be a fraction of elements of B. So. What's it now?
Either A divided B or B divided A.
Okay, right. So. In B. So that is either A over B or B over A is in if then done. What if not? If A over B is in B, then we're good to go. What if it's not?
Inverse.
Okay, if it's not, if A over B is not in A, then B over A is in B. Fine. Therefore, A over B is a unit in W. So what does that mean? What does that mean about B over A? B over A is in B, right? And it's also in UW. Therefore, B over A is in S. Right? So 1 over B over A, which say over B, is B over S. And then, any questions? Yes.
We can say that in the case that you're in the case that A equals 0, then W equals 0, and so it's in R. Is that because say A divides B or B divides A, you need it for say A.
Oh, are you thinking on me maybe if you're not being careful about A
Yeah.
not 0? Oh, we can assume that I should have just done this. We can also assume that A is not 0 as well. Because otherwise this is the 0 element, right? So I should have just written that down perfectly. Okay, others. Okay, so you might think about some of those other ones as well. Let me give you a big theorem here. We're going to use, and this is actually a key, this is a keystone for what we're going to do with connecting valuation domains to the notion of integrality. Theorem 414. This is a survival theorem, and I'll tell you what I mean by that in a moment. Let R inside T be rings. And U, a unit in the big one, U is a unit in T. And I, a proper ideal form. Then I survives in RU or universe. I've heard this clever. And let me tell you what I mean by survives. That is to say, either I or U strictly contained in RU, or I or U inverse. It's strictly contained in RU. What this means is this survives as an ideal. So in other words, if you take the ideal I and you push it up into RU, so you take all the elements in I and see the ideal they generate in RU, to survive means it remains a proper ideal. It doesn't ever pick up the one. It doesn't blow up the whole thing. Let me point out, of course, that I could survive in both rings, but it has to survive in at least one of them. And I love this proof. It's really, I stole this from complaints. He's always got complaints. He always had like really slick proofs like this. Let's suppose not. Okay. By the way, the opposite of surviving is sometimes called blowing up. Right. Suppose that I blows up in both these rings. That is, when you push I up into RU, it generates one. When you push I up into RU inverse, it generates one. So if not, then there exists two equations. And really, I mean, except for the fact that you're using a lot of letters, this is just really kind of high school substitution. It's a minimality argument. Let's see what we have this one. A0 is A1U. A1 with the AI in R. And B0 B0 inverse. The M U minus M is equal to 1.
I want those AI to be
I do. I want them to, and the B's. But yeah, they could be an I. We suppose that N suppose that N is at least as big as N, and if not, that's the neat thing about having a unit, we'll just exchange the role of U and U inverse. So we'll assume that n is greater than or equal to m, and we've made this choice to minimize the size of that equation. So, what we're gonna do is, let's multiply the second equation by u to the n. So. And what we get here is, well, let's just do it. B0, u to the n, plus B1, u to the n minus 1, plus Bn, u to the n minus m, equals u to the n. And I'm going to rearrange this. Notice I've got the same u to the n over here. So I'm going to get B1 un minus 1 plus B2 un minus 2 plus B n minus 1 Bn un minus m equals 1 minus B0. Now multiply this. Now we'll multiply this first one by 1 minus B naught. So. So I have 1 minus B naught times this big mess, A0 plus A1U plus AN UN equals 1 minus B naught. Right. So, anybody see what to do now?
Your substitution is the minus B0 UI and add B0 each side.
Right. So notice that this is, I guess I probably should put this out. This is 1 minus B naught, A naught plus 1 minus B naught, A n minus 1, B n minus 1 plus 1 minus B naught. Well, let's say, yeah, 1 minus B naught, A n U n is equal to 1 minus. Now, take this bit right here and replace it with this side of the equation. So I get 1 minus B naught A0 plus 1 minus B naught A n minus 1 U n minus 1 plus A n times this mess B1 U to the n minus 1 plus Bn U to the n minus m is equal to 1 minus 3. Everybody okay with that? What's the key observation right now? That is correct. We have an equation just like we have. Well, I guess we really need to bring this B0 over. But once we bring that B0 over, we have an equation equaling 1 of degree, and I use that term loosely, less than, right? And so there's your contradiction, and this establishes. So, must survive. In one of them. One of those two. Any questions? And of course, as I pointed out, it can survive in both of them. Take item zero ideal, it's clearly going to survive in both of them. Okay, any questions? Okay, this will be actually a key point here for times with integrality. So we'll pick up next time. See y'all later.